Good morning again. I had one more thing that I wanted to talk about this morning. It's this part of Dr. Physics A's video where suddenly he's doing a second derivative. I was surprised that there was a second derivative here because the equation it comes from doesn't have the derivative. Not a derivative of a Jacobian anyway. So I'm just going to take this second derivative here and reverse engineer it. This must have come from taking a derivative of the equation v sub m of y equals partial x r over partial y m v sub r of x. So that's this part and this part, and taking partial yn of both of those. But that equation that I just managed to reverse engineer is very similar to equation 3, but with one fundamental difference. Whereas equation 3 has a del y del x term, this equation has a del x del y term. In other words, equation 3 was a contravariant transformation, for instance, maybe a transformation of path elements, whereas this equation that we're now doing a derivative of is a contravariant transformation, perhaps the transformation of a differential of a vector field. In any case, when we do this derivative, the first step is to simply write partial over partial y superscript n in front of both sides. Now, once that is done, I'd like to try and figure out some arrows, how I'd like the output to be formed. So I'm going to try to get this to be an across vector, and maybe the m's can go down, and we'll see if we can get that to come out right. But we've got an across and down, and so we're going to have to do something else with the r. Whatever we do, there's going to be a third direction besides down and right. Honestly, my first inclination would have been to do something like this. That would have been all nice, but it would have led to a 1 by 1 matrix at the end, as we would have a 1 by 2, 2 by 2, and a 2 by 1. This would have ended up with a 1 by 1 matrix, and this would have ended up with a 2 by 2 matrix, and that can't be the case. But let's not worry about that yet. I'm going to erase that and first just use the chain rule to express this derivative of a product. So the derivative of this product is going to be equal to this times the derivative of this plus this times the derivative of this. Now, keeping in mind that I might not get this right on the first go, I'm going to attempt to do a matrix representation of this multiplication. Now, I'm pretty sure that if I've decided that my output is going to be down and right, that all my associated with m's and n's, that all of my m's should be associated with down, and all of my n's should be associated with right. And when I say I'm pretty sure here, it means that I currently have no idea. I mean, it's a total guess, but I know that it is either true or false. but I can use one clear example that I've had before to test this conjecture, and that was when I had t superscript m n equals a sub m b sub n. We went down with the m's, we went across with the n's, we go down with the a's, we go across with the b's. So I think this is a good criteria to use to decide the direction of the arrows. So I'm just going to erase that and then see what we can decide for the next set of arrows. I could have gone the opposite direction with the m's and n's. I could have had the m index increment across and the n index increment down. I might go back and do that after I fumble my way through the next decision of how to mark the r index. Mr. Intuition tells me I should mark this one double down and this one right. Same thing here, double down and right. Now, Mr. Intuition doesn't always lead me in the right direction, so let's see if that works. You're probably clear on the idea that partial y with the index increasing to the right will look like del y1, del y2. You might not have guessed that what I meant by the double down was to have a del x1, del x2 in a second pair of parentheses inside here, with the del y1, del y2 just going down in the first one, del y1, del y2, del y2. And then the v sub r will be fairly simple. V sub 1, v sub 2. And for the other matrix, it would look like, again, double down. So double down over down is going to look like this. As a matter of fact, it's identical to that. So I'll just copy it over. And now we see a place where Mr. Intuition steered me in the wrong direction. I can't have a matrix representation of a tensor with the two indices going to the right. This one needs to be down. So that will be going down with the v1, del v2, del v1, del v2, and then going across with the del y1, del y2, going across with the del y1, del y2. Now, with the benefit of the pause button, I'm afraid this is going to yield a 2 by 2 by 2 matrix. That's no good. Basically, I would multiply this by this. Actually, that's not even illegal. That one times that one, that's not legal. This one times this one, that's not legal. So let's erase that arrow and try and erase that matrix and try a double right and see if that works any better. Right, I want this in red. Red. Okay. So the double right over the right is going to look little matrix, two little right-hand matrices with a inside a larger right-hand matrix, which would be del v sub 1, del v sub 2, del v sub 1, del v sub 2, and then the single right is going to be del y1, del y2, del y1, del y2. Okay, so this one's better in one way, but it's worse in another. Yes, it's legal to multiply the 2 by 1 by the 1 by 2. It's legal to multiply the 2 by 1 by the 1 by 2, and this 2 by 1 by this 1 by 2, and this 2 by 1 by this 1 by 2. But guess what I'll get then? But that's going to give us a 2 by 2 by 2 by 2 tensor. So in order to do this right by matrix multiplication, I think we're going to have to commute these terms. We'll have to take that over there and that over there, bringing this back, and now we would have the sum 2 by 1 times 2 by 1 plus a 2 by 1 times 2 by 1. So let's just confirm whether this one is going to give us a 2 by 2 matrix. We would be doing this part first. This times this plus this times this. That would end up being a, let's see, this times this plus this times this would end up being a 2 by 1. So del squared del x1 del y1 del y1. Actually, is there a single option for how to do this, or two options? Option 1, I could take this times this plus this times this and put it here. And then take this times, whoops, this times this plus this times this and put it here. Or I could take this times this, put it here, and then plus this times this and put it here. The first option would have given me cross terms, things with both, with both dy1s and dy2s in the denominator. So that and this term with this term would give me y2 and y1 in the denominator. Option 2 would give me no cross terms, since I'm taking, with respect to y1, both the y1 terms, and with respect to y2, both the y2 terms. So Mr. Intuition tells me I should go with option 1 to make it as complicated as possible. Say del squared x1 del y1 squared plus del squared x2 del y1 del y2 del y1, and then the next thing will be using the lower part, so I can go ahead and slide that up or make that disappear. So this would be del squared x1 del y1 del y2. And notice that this is not commutative. You can't just say you can't just replace this with doing the partial derivative of y2 first and then the partial derivative of y1. This is going to be a completely different derivative than this one. But then del squared x2 del y2 squared del y2 squared. So that would be all multiplied by v1, v2. Oh dear, have I just really goofed? No, I haven't, because this is a vertical matrix. Okay, that's where I goofed, because this is a vertical matrix, this is a horizontal matrix. This is going to give you a 2 by 2 matrix when you finish up. Okay, and then I would just add on the multiplication of this, which is going to be del v1 del y1 times del x1 del y1 plus del... you know what? I'm not going to write this whole thing out. I'm just going to do the two products, this times this plus this times this. Is that... Well, that's bad news. Earlier, I thought this would come out to be a 2 by 2, but now it's starting to look like this will just become a 1 by 1. By putting this over on the right-hand side, I had a 2 by 2 by 2 by 2. By reversing those two, I just have a single scalar. So I've got to go back to the drawing board with this guy. Let's undo the thing I did with the commutativity and see whether we can set up something. Let's try to establish this exact same shape if we can. We probably can't. But I know I've gotten a 2 by 2 matrix just from doing something very much like this without doing anything special at all. Let's go ahead and use the commutativity and take a guess. Okay, that this needs to be down and this needs to be right. Down, right. Then I'll just erase all this stuff and see where that gets us. Because this is just going to be a 2 by 2 times a 2 by 2. Del v sub 1, del v sub 2, del v sub 1, del v sub 2, del y1, del y2 coming across, del y1, del y2 coming across, and then del xr coming across, del x1, del x2, del x1, del x2, and then del y coming down, del y1, del y2, del y1, del y2. Okay, so this expression will produce a 2 by 2 matrix when we're done with it, because a 2 by 2 times a 2 by 2 gives us a 2 by 2. It doesn't have any of those cross terms, or it won't in the end have any of those cross terms, because there's no... It's always y1 going across, y2 going down. So I don't really know for sure whether I did all this right, but I did manage to get a 2 by 2 matrix from both parts of the partial derivative of this. It seems like I'm not sure whether I created a unique representation. I don't think it was a unique representation, because you saw those options that I had right there. I'd like to find some better reason than just intuition, because my intuition is often wrong about whether to have those cross terms in there or not. But in general, I thought it was kind of an interesting method. If we've got a 2 by 2 by 2 tensor, something like this, I can elect to have things go like have a double down arrow or a double right arrow, and mixed with the right arrows and the down arrows in the matrix notation. So I know how to write a 2 by 2 by 2 matrix or a 2 by 2 by 2 by 2 matrix. However, I don't have established conventions for how to multiply matrices with more than 2 dimensions. we saw at least one case where the matrix multiplication representation had ambiguity. But I don't know for sure whether the ambiguity already existed in the Einstein notation, or if I created the ambiguity by trying to put it in matrix notation. If I created the ambiguity, which is probably the case, then it's really only a matter of finding the proper conventions for higher dimension matrix multiplication, which I can proceed to do as I have time.